So thanks for the introduction. And I'm Jackie. I'm a founding engineer at StarTree.
Hi, I'm Ron. I'm a software engineer.
So let me first clarify a little bit things. So obviously, we are not inventing the multi-stage engine, but it's our approach to expand the existing use cases for Apache Pinot. So let me quickly go over the agenda for this talk. So first, we'll talk about the previous major Pinot use case, which is the single-stage engine. And then I'll talk about the history of the query time join approaches. So basically, we try different things to do query time join. And then the next section will be like our latest approach, which is a multi-stage engine. And then we'll talk about the various performance optimizations we have done to make the multi-stage engine match the performance of single-stage engine. And then in the end, we'll leave some time for any questions. OK, so let's begin. First, I'll briefly talk about what is Apache Pinot. I guess there might be already several sessions talking about this, so I'll give a very high-level overview. So basically, Apache Pinot is a real-time distributed OLAP database that is designed for ultra-low latency, high-throughput user-facing applications. So to make this possible, we pick several design decisions. So first, it's a columnar database, and then we can do most of the index are pluggable. So all these plugging index techniques allows for rapid development of new index types. And then we can keep pushing the boundary of the performance. And then also, it is taking the Lambda architecture, which means it supports both batch ingestion and streaming ingestion. And then right now, it's capable of ingesting millions of events per second. Well, all the data will become queryable immediately. Then it's also highly scalable and fault tolerant. Meaning we have seen use cases where a single table can be scaled to thousands of nodes because the table itself is probably petabytes of data. And then it can be arbitrarily replicated. And then it also have fault tolerance, it has fault domain awareness. OK, so next I will talk about what is single-stage engine. So I'll start with an example. This is a classic LinkedIn use case where basically when I look at my LinkedIn website, I want to know how many users view my profile in the past month. So how do we get this translated into SQL world? So in SQL, I might be able to write this as a query select const star from I have a user view table where I want to search for my own view ID. And then I also want to put a filter on the view time. So pretty simple query, right? So let's see how Apache Pinot will execute this. So I will hide all other non-related components, but only show the query-related ones that are brokers and servers. So in Pinot, because it's Lambda architecture, we have real-time servers and offline servers, where real-time servers consume data from streaming, and the offline data, obviously, through batch ingestion. So let's say I'm a user. I send a query to the broker. Then for single-stage query engine, basically, broker scatter the query to all the servers, and then collect back the results, and then merge the results and send it back to the user. Pretty straightforward. So basically, Pinot is initially designed for this type of use cases, where it has a very powerful single-stage engine, and then it can serve this type of queries in single millisecond latency and thousands of queries per second. So if I imagine Pinot as something in real world, I would imagine it as a sports car, meaning it's just designed for high performance. It's designed to achieve the shortest lap time on tracks. So then what's next? I want more specific insights. For example, I want to know how many users work at LinkedIn viewed my profile in the past month. How do I do this? So obviously, I don't have the information from user view table who is a viewer, where the viewer work at. Then I'll imagine maybe I have two tables. One is user profile table, where I know the detailed profile of each user. And then I have a separate table, user views. And then in order to solve this query, I want to join these two tables together. And then I want to join two tables on the user ID, and then I want to look up some information from left table and some information from right table. And then, let's see, if I want some more specific insights. For example, I want how many users familiar with Java viewed my profile in the past month. So this seems similar to the previous one. And then also, for example, I want to know how many people who can help me get a job viewed my profile in the past 90 days. So this is actually a really LinkedIn use case where, like, if you're a premium member, you can see insights like this. And then next might be a little bit complicated, like how many people who recently changed their job viewed my profile. Because imagine, like, if I want to know who recently changed their job, maybe I need to do a self-join on the member profile table. So essentially what people are trying to do is expand the capacity of Pinot and then try to load a lot of boxes into this sports car. So let me talk about how, like, basically multiple approaches we tried to make that happen. So first is pre-join the tables. Basically, in professional world, is like denormalize the data. And then let's say I have these two tables. I have profile and views. If I pre-join them on the user ID, here's what I got. I got a table with view time, viewer ID, viewer name, viewer company, and viewee ID. So this one can be used to specify the query where, for example, like how many people worked at LinkedIn viewed my profile. So, but one thing we can find from this is I got duplicate like profile properties. For example, I got 2 records on Alice and 2 records on like company LinkedIn, which is like not necessary if I keep 2 tables separately. So basically the drawback for this approach is extra storage. And then obviously I need to maintain an extra ingestion pipeline to make this happen. And then also it makes changes on one table hard because basically all the changes need to be reflected to the pre-join table. Actually, this is the approach that LinkedIn took, and then it works well to some extent. But again, like for example, I can now use this like this approach to solve the problem where a user, like I want to know how many users who recently changed their job and then viewed my profile. Okay, so let's take it one step further. I want to do real query time join. What can I do? So first approach we took is called lookup join. Let's take a look how it works. So basically, I need to first load the user profile table onto every single server. And then I can look up the user's company from this like user profile table using the ID field. And then while I'm querying the user views table. Then in the end, after lookup, I can filter on user's company. Okay, sounds working, but what's its limitations? First, obviously I need to load the whole user profile table onto one server. And then I need, like basically if the table becomes too large, like it's no longer scalable. And then also I need extra storage to replicate this table to all servers. And then in the end, most importantly, like Pinot is so powerful because it has all different kind of indexing techniques. But right now I cannot utilize index to this lookup table because I need to first look up then filter. And then I don't know how to push down this filter to utilize the index. Okay, then we tried another approach as multiple single-stage queries. How does it work? So first query is similar to lookup, but I want to do the lookup step at runtime because I don't really want to replicate all the data. So I first send a query to the user profile table to get all the user IDs that matches my filter, company equals LinkedIn. The second query, I'll broadcast the result of the first query to all the servers, and then use them as filter for viewer, to filter on the user views table, and then to get the final result. Okay, so it also comes with limitations. For example, it's similar to the lookup approach, where like it doesn't scale if right side table is too large. Similarly, like if the first query result is too large, broadcast it will be super costly, or it will run into memory issues. So again, it's still not scalable. And then basically, because we need to broadcast all the results, so there will be network overhead. So overall, I would say all these approaches are similar like this. I'm trying to like carefully assemble all the boxes and then tidy it on top of my sports car. But it's not scalable. Like when I turn too quickly, it might fall apart. Okay, next, we think, okay, these approaches are not scalable. What about I use something external to help me do this? Right, so Presto, Trino, they're like quite mature like join engine that I can pick. So we do build the Presto Trino connector to help us solve this problem. So basically, we use Pinot as the storage, and then we directly pull data out of servers. And then basically, Presto and Trino connector allow you to push down certain filters, and then we can push down filters to accelerate the filtering phase. And then in the end, after pulling all data to the Presto or Trino node, we use their engine to handle the query execution. Again, it comes with some limitations. First, because we are using Pinot as a storage layer, mostly likely just the storage, so it's not able to fully utilize the power of Pinot. And then the control unit is actually sitting in Presto and Trino, so it doesn't know the detail of Pinot. So similarly, it doesn't know how to use the various indexing techniques within Pinot. And then also, like, obviously, we need to maintain a separate system. And then there are extra infra costs and management costs of that, like a separate Presto Trino cluster. So if I map this to real world, it's essentially something like this. Like I have a sports car. I want to use it to power, like to carry a lot of boxes. But then I lose my engine no longer work. I mean, I still have most of the power, but because of this trailer, I'm not able to like get the same performance. And then also because, for example, like the control unit is so far away from engine, it's not versatile, it's not it's not able to achieve a really good lap time, I would say that way. So what do we need? So basically, with all this experience and then lessons learned, we really need a joint engine that understands how to fully utilize all the indexing technologies in Pinot, and then know how to apply the most efficient index to get the best performance. And then we also need this solution to be flexible, expandable, so that it can be used to solve most of the user-facing analytics problems, because that's basically the problem Pinot is focusing on and trying to solve. Or essentially, sorry. we also need to minimize the overhead, and so that like we can still achieve the ultra low latency, high throughput requirement for Pinot use cases. So essentially what we need is a high performance SUV, where I can still get pretty good like record on tracks, but also I'm also able to daily use it. And I'm able to carry a lot of boxes with it. So now I will invite Ron to talk about the details of the multi-stage engine.
Thank you. All right, so I guess a little bit of instructions on this specific approach is that we wanted to talk a little bit more regarding to what we are targeting, right? So as Jackie mentioned previously, if you look at this approach, you have a trailer behind your sports car, you have to tune your sports car's engine for torque versus power or anything like that, but it's just not actually something you wanted to trade off, but it can actually achieve a lot of flexibility. You can have anything you want to put into the trailer, or you can go back to the renter to get a bigger one or anything like that. So that's super flexible. Having an SUV in this specific case is you're not going to put all of your boxes into it, but you can still put some, and the trade-off there is you're going to get a lot of like performance and powers, and it can get you pretty far. And also, not to mention, it's going to be super fuel efficient. All right, so let's go a little bit into, okay, there you go. Let's go a bit into the actual technological, like executional model differences, right? So in the very beginning, you have a sports car. You only do it once by singly gather your queries into different servers. Obviously, you have a broker there to basically reduce the numbers of the final results, giving it back. So obviously, the brokers becomes the bottleneck. Your single scatter cannot actually accommodate too much of the executional models. So this is what we want. We wanted to have an executional model that you can arbitrarily train as many of these single stages as possible. These are all hidden from the user. User can actually run whatever they want. The idea here is that if you look at the lookup joins or multiple single stage executions, it's essentially logically the same thing, but the difference is that you don't actually have to have your users or developers trying to stitch them together in an ad hoc manner, and everything just handled by the engine itself. So let's go a little bit back to the use cases. What exactly are we targeting? Like I said before, if you have a trailer, you can put whatever you want in it, but you can't do that in an SUV. So what do? So what we are actually targeting here is just the low latency, high throughput use cases with moderate amount of like query complexity, but you still want to make sure that everything finishes in real time, right? So all the actual complex, let's say multiple table, 3,000 lines of ETL queries, you're not going to be running that on Pinot. But we have our very specific targeting use cases in this specific design. So what we actually wanted to do here is get rid of the federated systems for these type of use cases, right? So for example, if you have a star schema joining, some of the things that you wanted to do pre-join, but you don't want it to pay the costs upfront for the ingestion, some of the aggregations or pre-cubing you don't want to do, then these are the new engines target. So how do we do it? Because the entire join is actually executing in Pinot. And Pinot is extremely fast. Everything is being done in a single scatter in the original day. So what we want to do here is we want to be extremely careful about what exactly we do on the join optimization strategy. First, we need to reduce the overhead. Like if you want to scan two tables, ship them over, and then trying to basically join them together, it's going to be super inefficient. So we want to reduce that. We also want to make sure that the data shuffling itself is actually being minimized. For example, if you really have too many data that you need to basically ship against each other, we want to make sure that that happens only when necessary. And we also want to make sure that the solution leverages what Apache Pinot is extremely good at. Like Jackie mentioned before, the single-stage engine provides a lot of pre-computations, pre-cubings, pre-indexings, and all of these goodies that you can actually use to simplify your join optimization. So let's use some typical example, right? So this is kind of like a simplified version or kind of an abstract version of the user profile versus the user view table. So if you have some kind of models, you want to count how many rows we're matching some filters between the table 1 and table 2, but I wanted to also group by some of the dimensions on the two and on the second table. What you typically do here is basically scan both of the tables. Hopefully you can actually push down the predicates, and then you can basically just do the shuffle joins on the next layer of the executional engine. So what we actually do here is we automatically do a predicate pushdown. So this is actually kind of like showing how Pinot's executional engine, the multi-stage engine, is actually turning this query into this type of like two-stage single execution. What we actually going to do here is we prepare a temporary view of the first table. You don't actually have to write it in this way, right? So it's automatically happening behind the scene. And we apply the predicates first. And then we basically come up with kind of like a temporary view of the first table in order for you to actually join it together with the second table. So once you've done that, what you actually do here is basically the second stage is similar to using the first stage to be your your future join. So for example, if all of your rows on the second table is going to be in your first table, you're going to basically stitch those two rows together, and this is your join result. What's better, even better is if you know that you don't actually care about the actual join exponential factor or quadratic factors there. For example, like in this case, if you have multiple join IDs that are like similar, that you can't actually apply this rule. But if you do, or basically saying that if your ID is actually a primary key, then what you can actually do here is essentially stitch the in clause there to basically use your first table's result as your join clause. So in this case, you can even use range indexer or even other indexing mechanisms in Pinot in order to basically speed up the join itself. So your join is not actually doing any hash, broadcast, sort, merge join, or anything like that. So next, going to reducing shuffle. So how do we reduce shuffling when it's necessary? So a lot of the things comes down to how you actually partition the data when you're actually putting these things into your servers, right? So for example, if your servers are randomly distributed, both of the tables are not collocated, anything, it's basically just like your out-of-the-box solution. It's going to shuffle a lot, right? As you can see here, only a handful of the actual data transfer is local. Most of the data transfer goes beyond the boundaries, going into network, et cetera, et cetera. But what if you know that there is a primary key that you're going to join like pretty efficiently, right? For example, the ID field. So in this case, you can basically just partition your first table into partition by your join key. And then you can actually drastically reduce your joining overhead in terms of like data shuffling. But the drawback here is you can actually just partition on one of the join keys. So you cannot actually do it for multiple one of them, right? And even better is if you know both of your tables are basically hashed by a specific join key, then what you can actually do here is put all of your join keys together and also make sure that your server assignment for those data are actually collocated. So in this case, you basically just eliminate the network. Everything is actually just local to local transfer. You're actually going to be much better off in these cases. Again, the drawback here is you can't actually do any flexibilities beyond the predetermined join key that you're actually doing there. And obviously, you can also leverage some of the things called pre-cubing. For example, like Apache Pinot has a pretty good StarTree index, so you can actually do a direct aggregation of lookups using the StarTree index. So what you can actually do here is, instead of doing kind of like a join and then trying to count the actual dimensions of the specific model, what you can actually do here is you can actually pre-count the numbers on your table 1, which is basically your left table. And the count is basically summing up into a pre-count number. From this point forward, what you can actually do here is on your join, you can actually just sum up the counts, right? So it's kind of like summing up the counts in the two different stages in that kind of like a two-phase fan out. It's going to be giving you much better performance because of the pre-count is actually done in the StarTree index. So all in all, let me summarize this. What we are actually building here is an engine that is highly leveraging Pinot's performance characteristics. We are not actually trying to tackle super complex ETL-like queries. It can. It's not going to run extremely efficiently. It's not going to actually give you the best performance. But as long as the query can actually leverage whatever Apache Pinot is super good at, this is the way to go. A little bit of like a caveat or kind of like a design choice that we did here is the query flexibility here is super nice. We don't do a lot of super heuristic optimizations for your query engine, for the query that you actually provided. Instead, what we do here is we run a relatively simple query optimizer, but we are relying on the user's knowledge for giving us like hints regarding like how do we want it to optimize the queries. For example, in this case is we can either do this in-clause join as a dynamic filter. Basically, you push one table to another. If you know that the second table is going to be super small compared to the first table after the filter, or you can actually basically just do it in kind of like a normal hash join. So hints basically lets users control exactly what the query is supposed to be. And second one is it makes our optimization life much simpler. That's one of the reasons why it's still keeping it extremely fast in terms of query planning plus its executional time. There you go. Okay, so what's the catch? One thing I wanted to emphasize is it's not a Presto. It's not a big query. You cannot reuse a multi-stage engine to run all of your ETL-like queries, like I said before. But the idea here is that as long as you leverage the Pinot's executional characteristics, you can actually write pretty complex queries and it can run pretty well. It's just that the knowledge base is basically given back to the users to basically put in all the query hints, making the query flexible, but at the same time, it still leverage Pinot's optimization and the characteristics. So again, it's also optimized for user-facing analytics. So a lot of the query patterns that doesn't seem too complex, but the query pattern is not actually fitting with the analytics user-facing, then it's not something that we're currently optimizing or tuning it for. And also, it's not optimized to save memory. So in order to achieve the maximum latency throughput that we can, we use as much memory as we can in order to finish your query as soon as possible. So that's sort of like the trade-off there. So if you launch an ETL-like execution that you have a lot of boundary weightings when you transfer the data, then your memory is going to explode. It's probably not going to be super efficient. So yeah, so this summarizes what I just said. So we wanted to stick this multi-stage engine into somewhere between what you wanted to do in terms of trading off your pre-query complexity versus you wanted to use something extremely flexible by utilizing Pinot as kind of like a table source. Something in between, but we wanted to make sure that it leverages what Apache Pinot can be done in the most efficient manner. I'm going to complain about this a little bit. But yeah, so here is one of the performance measurements on one of our use cases regarding how we optimize the queries from more than 120-second latency that we can't even finish the query because it ooms out, into somewhere that we can actually run within 0.5-second latency, right? So we have some baseline hash join results. You're basically not optimizing anything. Afterwards, we can actually optimizing the join by leveraging some of the characteristics of the data. We wanted to also optimize the layout of the data by pre-partitioning the data itself. We wanted to push down the aggregates beyond the join so that you can actually leverage StarTree index. We also want to make sure that the partition-aware computation is there so you can co-locate the servers, et cetera, et cetera. So we have a lot of these optimizations that can bring a simple hash join down to, we would say 200 to 300 times faster than its original speed. So yeah, we wanted to open up the floor for Q&A because I covered most of the high-level basics. So I'm sure there's a lot of questions, so I wanted to open up the floor.
So if I understand right, the joins between offline tables and real-time tables is possible, right?
Yes. So the engine itself does not differentiate whether your data is located on different tiers of servers. To the engine itself, it's basically just like, hey, here are a list of segments that contains the data you want. And then we will basically just pull these servers to run the first stage, which is like the leave stage of the engine. Mm-hmm. So it doesn't really matter whether it's real-time or offline.
So kind of tangential to this one, if there is a use case where I have the offline table, is it possible to convert that into a real-time table?
Can you repeat the question again? You wanted to convert?
An offline table into a real-time table.
To speed up the query or?
So say we started with some experimental data and we cannot wait for the whole data to be streamed. So we just started with some initial data set into an offline table, but we want to use this data to be combined with the streaming data that is coming in. So we want to convert that into a real-time table and then start streaming the data into that.
I see. So let me clarify if I understand your question clearly. So you have some data coming into the real-time table, but you are not waiting them to come in yet. You wanted to have the offline table to be pre-ingested with something that you already have.
Yes.
And once this experiment is done, you want everything to go back to the real-time tier.
Yes.
Is that correct?
Yes.
I can probably take this, yeah. So there are multiple, again, Pinot is very flexible. It has like Lambda architecture built in. So there are multiple ways to do this. For example, like if you are utilizing the Lambda, like we have the merge of offline table and real-time table. And then that is called hybrid table, where basically offline table stores your historic data, and then you also have a streaming ingestion, right? Go to the real-time table, and Pinot will automatically handle the merge. Basically, you won't see like duplicate data, because we make sure only one copy is queried. And also, like for example, if you know I want to bootstrap my real-time table with some batch, like for some offline data, and then after that I want to ingest, then we also support directly uploading the batch ingested segment into real-time table. Then if you use this mode, then there's no like special handling of querying only one copy, because essentially it's one real-time table, but it's doable. So basically you first bootstrap your real-time table with your offline data, and then start, for example, Kafka, and then make it point to the Kafka, then it works. Does this answer the question?
Yes, so how can I change it, like from the API standpoint or from query console? So what is the interface I could use to change this declaration of offline to real time?
I mean, do you have, for example, a streaming ingestion available?
Yes.
And then does it have the same data as the offline
Yes.
table, or
Yes.
if you already have everything in the real-time stream, you just create a new real-time table and then stream from the start. Then it'll basically create a new table with all your offline data and also the new streaming data.
That may not be quite possible, but yeah, I can take that offline.
Yeah, you can find me on Slack. And then we can talk
And then
about
obviously one of the things I wanted to emphasize is that the real-time table and offline table are technically like the physical ones, but there's a logical wrapper around on top of it to basically split between the real-time and offline part of it, so that there's kind of like a time boundary between them. So for the actual executional engine, you can actually select start from the real-time part of it, select start from the offline part of it, but you can actually select start from the logical table, which it automatically does this bit for you.
I just had a question about what's the state of the multi-stage engine in 1.1 versus 1.0, and like, are there like big features planned that are missing, or is it completely like feature complete?
That is a good question. So I guess like for the 1.0 release, what we wanted to really emphasize there is the stability and the usability and performance of the multi-stage engine, specifically for join queries, right? So there are a lot of new use cases, specifically if you think about a lot of the analytics or user-facing analytic use cases, we have like window functions, complex event analysis, and all of these features are actually in plan. And there are a lot of other feature in terms of like SQL features that we wanted to also add as well. So that's in terms of features. And yeah, I'm not sure whether that answers your question, but that's sort of like how we plan out through the post 1.0 release. So as we go with 1.1, 1.2, 1.3, these are the features that we want to get in. And obviously we want the community's feedbacks regarding what are the most important ones, so in order for us to prioritize the workflow.
Thanks. And one other question is just, how do you envision like the Trino connector, for example, integrating with the multi-stage engine? Will it know to like push down queries, like effectively push down queries directly to Pinot, or is that something not planned yet?
Yeah, so that's a good question. So let's go back to, where is it? Yeah. I really need to complain about this, but yeah. So basically, the goal here is a little bit exaggerated on this page because we want to kill the federation system. But technically, no, we don't want to kill it. You can still run it for the complex ones that we cannot handle, right? So if they are not user-facing or anything like that. So the idea here is basically how do we gauge the difference between whether you wanted to plug in an external system to do all of the complex and more resource-efficient use cases. So like, I actually developed some of the features on the Trino and the Presto Trino Pinot connectors. The idea is that, let me put it this way. So the idea here is if you cannot leverage, if there is still things you can squeeze out from the Pinot engine in order to do your transfer from the source connector layer all the way to the Presto Trino connector layer, then it's better off to write that into the multi-stage engine approach. It's only if you exhaust that approach, for example, like you have complex multi-dimensional tables that you cannot actually pre-allocate some of the partitions for multiple one of your queries. For example, you have user ID, you have content ID, you have promo ID, you have all these other like columns that you want to join on, then you need to pick one, right? But that one can run on multi-stage engine pretty efficiently, but the rest of it, well, we will need to profile, we need to see how it goes. So that's sort of like the one approach. The second one is obviously there are a lot of like, I would say, yes, they are user-facing analytics, but they are not actually fine-tuned or optimized right now for multi-stage engine. These are the things that we wanted to look for in the future. So the borderline basically just draw up and down depending on the development of Pinot as well as the development of the external query federated system.
Yeah.
Thank you.
And also, like I would like, from roadmap perspective, so I think our plan is within this year, we want to make multi-stage engine the default because it's capability. And then also, you mentioned that like Trino Presto like connector. So you want that connector because there are feature gaps, right? So ideally, we want to fill all these feature gaps. So basically, the multi-stage engine itself serves as Presto or Trino. But before that, I think it's definitely like possible to make the connector directly query the multi-stage engine. Because basically, when we make multi-stage engine default, it will query the multi-stage engine, and then basically more queries can be pushed down. And then, for example, simple joins can be done on Pinot side and then sent back to the Presto node.
I have a question. So you talked about co-location across two tables. How do you configure that? That's interesting, or is it something done automatically?
Yeah, good question. So there are two questions on collocation, right? So one is partition, one is collocate. So the first question is how do you partition the data, which is basically defined by the user. And the collocation is automatically happen if you want to configure that, hey, I want these two tables to be collocated, and Pinot is automatically figuring out where the segments, the partitions, the files needs to go to which server. So that's sort of like automatically handled. But essentially, it is the user's choice to basically determine what exactly is the partition scheme we want to use for each one of the tables. And obviously, for example, if you want A to collocate with B on key A, and then B to collocate with C on key B, obviously this is not possible. So that's sort of like the limitations there.
Thank you.
Yeah. High level is Pinot will automatically figure out whether it's co-located, then pick the best approach.
Yes.
Okay.
Oh, yeah, the question is, do you have a limit on number of tables you can join? The answer is no. You don't really have a limit there. As I mentioned before, literally speaking, you can chain as many of these multi-stage like blue boxes there as possible, so there's no limit there. The real limit is actually whether you can efficiently compute them without like blowing up the cluster's resource.
Hi, just two quick questions. So you mentioned the multi-stage uses more memory. So when, I guess, configuring or tuning Pinot, should we increase the heap or the off heap for that? And secondly, it's just the join options, super interesting. What's the best place to find out more about the available join options?
Okay, so first question is like memory. So in multi-stage engine, we are building basically the same mechanism to do memory protection. So essentially, it should be the same as single-stage engine. The reason why we said it might utilize a lot of memory is like in the intermediate stage. For example, I need to shuffle some data. Then the data is like, actually, when it's just released, the whole data is stored in memory. Then at that time, we need a lot of memory. But we have been making optimizations. And then right now, it's using streaming. So basically, we only hold one block of data in the memory. And for join case, because after hash join, like we need to hold the right table in memory. So, but also we build some like protection. For example, we limit the total number of rows on the right-hand side, and then if you go over that limit, we can, like, basically it's all configurable. It can throw exception or it can continue with whatever we get. Or you can increase your limit. So basically it's tunable and then it should work well with your existing configuration. What's the second question? Sorry.
Yeah, what's the best place to find out more about the available join options? So we can provide
I see.
hints.
So it should be available in the Pinot documentation. And also, like, from roadmap perspective, we are trying to slowly remove these options and then make Pinot smart so Pinot can make the best decision. But it takes time. So as we iterate, you might see, like, sometimes we add some new option and then remove them. But eventually, in ideal world, Pinot should be smart enough to figure out how to do the join most efficiently.
Yeah, just to add a little bit to the first question regarding the memory management is that if you think about how, say, Presto or Trino execute their models is they split the entire execution plan into fragments, and each fragment are basically just kind of like coordinating with the global coordinator to see if I want to schedule this or not schedule this. It doesn't happen in Pinot. Pinot actually schedule everything all at once in the very beginning. So therefore, if you think about, like, if we wanted to do a streaming execution on joining A, B, C, D, E, F, G, like many, many tables. So each one of these joins are actually opening up the join buffers for accepting streams. So depending on how your join speed are being executed faster or smaller, like all of these data exchange blocks in the boundary would actually hold some of the buffers. So that's why the more you join, the more likely you're actually going to have more memories to consume. Again, that's one of the reasons why I said that the resource management is geared towards throughput and latency, but not geared towards resource efficiency.
I have a question. If you pre-schedule all the work, how resilient is this architecture to failures?
Can you say that one more time?
How resilient is this architecture to failures if you schedule everything on the planning side?
Yes, at this moment, I think at least for the 1.0 release is we don't support failure recovery on the partial block. You actually have to restart the entire thing. So the entire execution graph is one schedule, one deployment, one startup, and one failure. So if there's a failure, you need to retry, you retry for the entire block. So there's no cross boundary executional block communication saying that, hey, if this fails, I need to start, like let's say stage 3 fails, so we want to start stage 3 prime, that still connect back to the original stream, but I mark my data as like, hey, this comes from a prime stage, not the original stage, and then your deduplications on top of the logic is actually kind of handled to basically discard what I already have, which makes the executional engine more complex, which also adds latency and throughput issues. Yeah.
Actually, it's not that bad if you think the whole query run probably 1 second.
Exactly.
So just retry everything, or we don't want to really complicate the engine to handle all the retry because that logic itself might be more expensive than the whole query execution.